Are we rolling? Okay. So what I did in the previous hour, sort of sneakily, I already proved that there is no choice function for this set of pairs. So just let's have a look at the situation again. Countably infinite set A, we have split it into pairs, and this is our group. These are our supports, the finite subsets again. And the sequence of pairs belongs to the symmetric submodel, the permutation model. We need that because otherwise I know it. Okay, so now suppose we have a choice function. So we take support for F, so that abbreviates what I had on the board a few times. If pi fixes AI and BI for every I less than or equal to k, then pi also fixes F. And now, of course, we're in trouble. What I showed in the previous hour was that actually the range of F is part of its support. But let's do it according to how Fraenkel did it. Look at the value of F of at k plus 1. Well, it should be the A of k plus 1 or the B of k or k plus 1. So again, there's not much exciting algebra going on in this type of argument, though. Basically, all we do is flip pairs, and that's about it. So again, we just flip these 2 points of A, and well, pi of F is equal to F, but we know that if we take the pair k plus 1 comma A k plus 1 and we let pi work on it, act on it, then the first coordinate stays the same, but the second coordinate changes from A k plus 1 to B k plus 1. So the f of k plus 1 cannot be either because if it was one of them, it was also the other one. So no, this is not a choice function. It fails just right above its support already. By the way, this,
Sorry, this is probably, I've missed something, but I'm unsure as to why our choice function can have omega as its domain. I'm unsure why our choice function can have omega as its domain, because it needs to take elements of the sequence and map it to their own elements.
Yeah.
But they aren't, like, the elements of the sequence aren't in omega. That's not doesn't seem like it matches up. The choice function should take bits of the sequence and pull out one of the two elements of it. But instead its domain is just straightforwardly omega, which isn't like the sequence is other things, they're subsets.
This is what I mean by choice function.
Okay.
I didn't quite get what you...
I thought a choice function had to start, for a choice function for the sequence should take as its arguments the members of that sequence.
Well, okay. But I just translate that to a function with domain omega. There is no big difference there.
As in, the function would go like from omega to the elements of the sequence to.
I mean, this is a bijection between omega and the set of pairs.
Okay.
So I just compose that bijection with the f that I'm talking about, and then I would have had a choice function. Because the point is, Pn goes with n. And n goes with the choice, so Pn goes with the choice as well. Yeah, you're right, I think. But there are also indexed versions of the axiom of choice where you are given an indexed family of sets and then the choice function has the index set as its domain. So technicality, I think. Okay, well. Great minds think alike, apparently. So anyway, either if you take the set of pairs as its domain or omega as its domain, there's not going to be a choice function. What else can we say about this model? Actually, quite a lot, as you will see in the homework, which I plan to post tonight. For example, the set of atoms is still Dedekind-finite, but the power set no longer is. And I'm not going to give that away because that's part of the homework, although it's not very difficult. So this model shows you that a Dedekind-finite set can have a Dedekind-infinite power set. Of course, if the power set is Dedekind-finite, then certainly the set is Dedekind-finite. So that implication doesn't reverse. There is a stronger version of, say, quote-unquote finite that this set also has, which is also implied by the Dedekind finiteness of the power set. So there's actually a distinction there as well. And you can do many more things with it, but I'll leave that for you to discover from the homework. Okay, let me give one thing away. You can show that you can dualize Dedekind finiteness. If you think back to linear algebra, if you had a linear map from Rn to itself, then it was bijective, if and only if it was surjective, if and only if it was injective. It's the invertible matrix theorem or something like that. Okay, so you can also define finite to mean every surjection from the set to itself is injective. That's sort of the dual of Dedekind-finiteness. This set has that particular property as well. If you take a surjective map from the set to itself, then it happens to be injective. That's also part of the homework, by the way. All right. Okay, I think I'm not going to finish Mostowski's model, so that'll be part of it next week. So what do we have? We have Fraenkel's two models. One, the set of atoms doesn't have even a linear order, leave it on a well order. Two, we have a set of pairs without a choice function. So we have killed the axiom of choice, so to speak. But in the investigations into the axiom of choice, there are all kinds of questions that pop up. Okay, well, how much choice is needed for linear orders? Because apparently it is not a given that an arbitrary set has a linear order. Apparently you cannot prove from ZF, as we will see later, that any arbitrary set will have a linear order. There is actually a model of set theory, nice enough, where the power set of the real line doesn't have a linear order. So there is no way sort of to try and compare all the subsets of the real line by saying, well, let's put them on a line. There's always going to be things that are against that. They'll be fighting against it. There is a model where that's impossible. So there is a bit of choice going on there as well. And there's all kinds of implications between some of those major statements that people have been trying to sort out. And the permutation model technique really helps. Okay, we can make a permutation model where, for example, there are some ultrafilters, but the axiom of choice fails. There could be models where there are no ultrafilters, but still there is a bit of choice left. There is also, it's one of these three that I'll be talking about. There's also a model where there is a metric space and a function that is sequentially continuous but not epsilon delta continuous. So that one of the very first theorems that you did in analysis 1 in your first year or something like that, even that uses a bit of choice. And when you go back to that proof, you will see that there was one point where basically every book sort of bullshits you and says, oh, here's the sequence, when it's not there. What the book only did was show that each individual set in a sequence is non-empty. It didn't really say that there was a choice sequence for that family of sets. Anyway, we're going to stick with linear orders and such. And before I start, I want to make one or two general remarks about supports and classes. I assume that, I think classes were talked about in the lectures before, right? So you can do set theory with classes as legitimate individuals. But that's not ZF or ZFC. ZF only talks about sets. So classes formally don't exist. They're just abbreviations a class is basically an abbreviation for a formula, and you wonder, okay, why should I abbreviate a formula? Well, the reason you want to introduce classes and talk about them is because they make life a little bit easier. So one thing that I've used is on the class of ordinals. Now, if you want to write down what it means to be an ordinal completely in the language of set theory, you'll get a pretty long formula. Because you have to express that the element of relation is a linear order, and you have to express that it's a well order. Yeah, it's just a lot of work. You can say, okay, I'll call that phi and be done with it. But then you say, well, every ordinal is of this or this type. And then you can express that as an implication, but you can also express that as an inclusion. Every ordinal has this or that property. Very often you can say, oh, the class of ordinals is a subclass of that thing. And it's just nice to be able to formulate stuff like that. But in the background, there is always the formulas that define the classes. But for example, if you do the recursion theorem, it's much easier to state the recursion theorem in the following form. If I have a function from the universe to itself, then there is a function from the ordinals to the universe that satisfies the recursion properties. It's nice, it's pictorial, you can sort of feel what is going on, you get a feeling for that. But if you want the formal statement of the recursion theorem, it simply says, if I have a function if I have a formula that seems to define a function in the sense that for every x, for every y, for every z, if phi of x, y holds and phi of x, z holds, then y is equal to z. Which is way more talking than it's a function. Then there is another formula where the first coordinate is always an ordinal, it looks like a function, and it satisfies this, that. That's just cumbersome, and looking at having classes at your disposal makes life a little bit easier. And so okay, we're going back to the filter language for a moment. We can call a class C symmetric if this happens. Now, generally you sort of feel, yeah, okay, I think I know what you mean. If x is in C, then pi of x is in C, and there is also always a y such that pi of y is equal to x. It has to be injected, it has to be a bijection between C and itself. strictly, formally speaking, we want this. This and this basically means the same thing. Yo.
Do we still have to take the permutations from G?
Of course. So if we want to talk about symmetric entities larger than sets, we usually take the language of classes, but behind the scenes, we should always think of it as in terms of formulas. Yo.
If phi has any parameters, do they commute with it, or do we just take
No. Because the P acts like a constant in the definition of the class. So if you have parameters in the formula, so the class is defined from the formula and one or two fixed sets, then of course those fixed sets stay fixed. You're not going to permute those because you want the class to really depend on the elements that you have in mind. So if you do parameters, the parameters stay the same. It's the members of the class that are going to be permuted. That's a good point. Maybe I put it on my notes. No, I didn't. I forgot to put it in my notes as well. Anyway, why do I bring this up? Because we're going to be needing this idea in a special case. Suppose we start with a set of atoms and an ideal. We can look at the class of all pairs, x comma e, where x is from the big universe and e is from the ideal I. And we can say, well, e is a support for x. If x is not symmetric, it doesn't have a support, so there are no e's. So this is only interesting for the x's that actually are symmetric. But we can simply define it like so. if you have a subset of, if you have a member of the ideal and you permute it and you look at all the things that fix it, we calculated this in the previous hour. You conjugate the thing with pi and pi inverse. If you permute, if you take an x and you take its image under pi and you want the symmetry group of that, then you get this. You simply calculate those things and it's conjugation, what is going on there. So, yes. Because E is a support for X, has an easy definition. It's just a subset relation between the two groups. And so if E is a support for X, then the fix of E is a subset of the sim of X. But if I do the conjugation bit, it preserves the subset relation. So there, back and forth. Now, we're going to the Mostowski model, and there, this class is going to become important. We really want it to be symmetric, and we really want. And we only look at the pairs that, of course, are in script V cross I. And we really want it to be symmetric, so that's why I made the point of mentioning that. When you download the notes tonight or tomorrow, you will find that these are among the longest that I put on the website because there's lots to check in the coming model. Okay, so this one is called this one is called the ordered Mostowski model. It was constructed by Mostowski in answer to a question of Fraenkel's, and I mentioned that a few moments ago. We create a set of atoms that cannot be well ordered, but we do it in such a way that the whole universe has a linear order. So what I said in the previous hour, every set has a has a linear order, sorry. Actually, in Mostowski's model, the whole universe has a linear order. Therefore, every set is linearly ordered as well. We need to assume, I think Jech in his book forgot to do that explicitly, we do need to assume global choice. I don't know if that was discussed, but you can have global choice, which means that you can well order the whole universe with one relation. Fortunately, that's consistent because it's true in Gödel's constructible universe, for example. So we're not going to do something silly today. The ordered Mostowski model, okay. Just wanted to check if you know your classics. Everybody knows what type eta is? So you don't know your classics. It's the order type of the rationals. That was Cantor's notation in his big last paper, where he was summarizing all his work, where he showed that every countable densely ordered set without maximum or minimum is isomorphic to the rationals. And that common order type he called eta. So, and of course, we can do that in our universe V. Why not? We just take the rationals and say, well, those are the atoms, and be done with it. So we have two ingredients in our model to begin with. We have the atoms, we have a linear order. Our group is still, of course, going to be a bunch of bijections, but they're going to be all the automorphisms of the linearly ordered set. All the isomorphisms of the linearly ordered set to itself. In other words, all the order-preserving permutations. Notice the symmetry group of the linear order is the whole of G. Because if I take the image of the linear order, the set of ordered pairs that make up the linear order, remember, a linear order is a subset of A squared. And I let pi act on it, pi preserves the order, so every pair xy with x less than y ends up being of the form pi of u comma pi of v, where u is less than v, and vice versa. So this one, and because the rest it's ordered pairs of atoms and everything, the order is already in the permutation model. Because the ideal is very boring, but we only do the finite sets again. See if I can find examples where there is something more exciting going on, but most of the stuff that we've done here is just using the finite sets. This is it. We take the order-preserving bijections, we take the finite sets, and that will give us the model. Okay. Now, from the homework, or I think from what I said last week, what is the fix of A? The fix of A is just the identity map and nothing more. That's not in our filter. So A has no well order because its fixed set is too small. So the only thing, quote unquote, what we have to do is show that there is a linear order of the universe script V. That is going to be a bit tricky. see if I. Okay, well, let's see how far we can get. Main property of the supports is this. Suppose you have, why not? Suppose you have two supports for your set X. What is obvious is that if I have a support and I make it bigger, it's still a support. Because the bigger the set gets, the smaller the fixed group. But what happens here is something else. I have two possibly quite large sets. Both act as a support for X. And then I say, oh wait, look at the intersection. That's still a support. And it's conceivable that although E1 and E2 both have plenty of points, the intersection could be just a few. And still, that intersection is also a support for X. I think given the time, okay, you can study that in the notes, but I'll talk about it next week. What's behind, okay, here is where the algebra gets a little bit more interesting. Okay, this is sort of a universal notation. This is the subgroup generated by these two sets. If I take the fixed subgroup for E1, union the fixed subgroup for E2, and I let it generate a subgroup of G, guess what? That subgroup, that generated subgroup here is just the fixed subgroup for the intersection. And this is where the work is. When you read Jeff's book, he sort of chickens out and says, oh, draw a picture to see that this is true. And I tried to draw that picture and I couldn't get anywhere. It took me way more time than just a picture to get this done. I had to go back to Mostowski's paper to see what was going on. Yeah.
And is this true in general or only for finite sets?
For finite sets and in this particular case. So E1 and E2 are support, so they're finite sets. And if I take both the fixed subgroups, take the union and let it generate another subgroup, I get exactly this. I mean, this is clear, but this is a subgroup of that. Because if I fix E1, I fix this. So this fix is a part of that, this fix is a part of that, so whatever they generate is going to be part of that subgroup. The point is, if I have a permutation that fixes only the points of this, can I write it as some sort of composition of things here? And that's where the work is. But the consequence of this is the consequence of this is that every element has a smallest support. Why? Well, take a support, intersect it with every other support. That's a family with possibly empty intersection, but just take the intersection of everything you get. That's going to be a support, because by induction, if I intersect 20 supports, I still get a support. And I have a finite family of supports to work with if I fix this one, and that intersection is going to. So it's possible that X has two supports, one over there, and the intersection is empty. Then apparently the whole group, the empty set, is a support for X, and it's apparently the whole group is the symmetry group. That's a special case, and that's actually the most difficult case, or what shall I say, the easy or the more difficult case, depending on your point of view, is start with disjoint sets, look at this thing, and find that it's the whole group. Once you know that, you can build this intersection into the whole affair, but I'll be talking about that next week. Now, very roughly, and I'll get to the rest next week. Where does the linear order of the universe come from? Well, we have this. We had our symmetric class of all the support pairs, but this is a subclass of that, and it's also symmetric because the thing that we did preserves all the orders. So if the smallest support exists and I permute, I get a smallest support for the permuted element. This is a class that is symmetric, and all the members, so it's hereditarily symmetric, so it's a proper nice subclass of the script V. The set, the family of finite subsets of A has a linear order. Lexicographic. You take their characteristic functions, you look at the first place where they differ. Because of finiteness, there's always a first place, and 0 or 1 tells you which one comes first. Next step, I can take for every X, I can take its orbit. I simply chase it around under G. That orbit has the whole group G as its symmetric subgroup, as its symmetric group. That means that I can well order the set of orbits. Because the fix, okay, the class of orbits, its fixed group is the whole group. Belongs to the filter, so it has a well order. Okay, so how do I linearly order the universe? I look at, say, the ordinal number of the orbit of X. That's my first criterion. So I have a pair X. I have a pair x comma e and y comma f. It could be that the orbit of x comes before the orbit of y. Then I know that this one comes before that one. If they happen to be the same, then y is a permutation of x, but f is the same permutation of e. And one of them comes before the other in the order. Because there is one more thing, that if you know that pi of e is equal to e, then pi is in the fix of e, because of the order preservingness. So we really do use that linear order of the set of atoms. And so we have using these pairs, we have a lexicographic order of the whole universe. And okay, I'll fill in the details next time because it's getting close to 4 and maybe Ned has a few wise things to say about the homework. Not impossible, okay. Okay, so I'll leave it here. I'll finish this story next week. And then I'll try, I want to do 3 things. And we'll see how whether time lets me do that. The Mostowski model can be used to show that there is no cardinality function consistently, and I would really like to show that's we use the axiom of choice for that using the ordinals and everything, but there is a model where there is no cardinality function, and you can use the Mostowski model for that. And I want to talk about the consistency of what we have been doing, what I mentioned a few moments ago, showing that there is a model where this ZFA holds based on a model for ZF or ZFC, and to try and give an indication as to how we can transform this into consistency proofs for ZF itself. How can we represent the atoms in a normal model for ZF with regular sets and everything? That's my plans for the coming 3 classes, and we'll see.
15 minutes.